Hello, this is Difficulty Math, and in this video, we're gonna solve this integral. The integral from 0 to pi over 4 of square root of tangent of x minus tangent of x squared dx. So we will solve this integral, and well, first let's make the substitution t is equal to tangent of x. And well, after substituting t is equal to tangent of x, we get the integral I here. Let the integral I be the integral from 0 to pi over 4 of square root of tangent of x minus tangent of x squared dx. Then after substituting t is equal to tangent of x, so dx is 1 over 1 plus t squared dt. Then we get I is equal to, tangent of 0 is 0, and then tangent of pi over 4 is 1. So integral from 0 to 1 of the square root of t minus t squared over 1 plus t squared dt. So that's after we substitute t is equal to tangent of x. And then, using the geometric series, 1 over 1 plus t squared is equal to the sum from n equals 0 to infinity of negative 1 to the nth power times t to the 2nth power. And this geometric series converges for t is less than 1. And then, well, we'll substitute this geometric series into this integral. Then we get this. So the integral I is equal to the integral from 0 to 1 of, well, the square root of t minus t squared, times 1 over 1 plus t squared. So we substitute the geometric series into the integral, and we get times the sum from n equals 0 to infinity of negative 1 to the nth power times t to the 2nth power dt. And then interchange the sum and the integral, because this series converges for t from 0 to 1. For t from 0 to 1, it converges, the series converges. So we can interchange the series and the integral. So the integral I becomes the sum from n equals 0 to infinity of negative 1 to the nth power times the integral from 0 to 1 of t to the power of 2n plus 1 half times 1 minus t to the power of 1 half. And this is just because, well, the t minus t squared here is t times 1 minus t, and square root of t is t to the power of 1 half, and then times t to the power of 2n, so it's t to the power of 2n plus 1 half here. And then we have so t minus t squared is t times 1 minus t, and then the square root of 1 minus t is simply 1 minus t to the power of 1 half. And so that's how we get the integral here. So then next, let's solve the integral inside the series. And well, so we will use the beta function. So the definition of the beta function is, well, not the definition, but a definition of the beta function is, because the beta function can have many definitions in many different forms, like it has at least 3, I guess. Anyway, so we will use a definition of the beta function, or more precisely the Euler beta function, to avoid confusion with the Dirichlet beta function. But anyway, so using a definition of a beta function, beta of u and v is equal to the integral from 0 to 1 of t to the power of u minus 1 times 1 minus t to the power of v minus 1 dt. Then this integral, the integral from 0 to 1 of t to the power of 2n plus 1 half times 1 minus t to the power of 1 half dt is equal to, so this integral, using this definition of the beta function, that integral is equal to the beta function of 2n plus 3 half and 3 halves. So the beta of u and v is equal to the integral from 0 to 1 of t to the power of u minus 1 times 1 minus t to the power of v minus 1. And so here, this is the u here. The u here is 2n plus 3 halves, and the v here is 3 halves. So t to the power of 2n plus 3 halves minus 1 is 2n plus 1 half, and then times 1 minus t to the power of 3 halves minus 1 is 1 half. So this integral is equal to the beta function of 2n plus 3 halves and 3 halves. Then, using the relation between the beta function and the gamma function, beta of u and v is equal to gamma of u times gamma of v divided by gamma of u plus v. Then we get, I'm gonna go to the next slide. Alright, then we get this integral is equal to the gamma function of 2n plus 3 halves times gamma of 3 halves over gamma of 2n plus 3. So that's just using the relation between the beta function and the gamma function. Then, so now we're gonna simplify each of these gamma terms. And then, so using the recursive relation of the gamma function, gamma of u plus 1 is equal to u times gamma of u. Then, well, and using the special value gamma of 1 half is equal to square root of pi. Then gamma of 3 halves, which is gamma of 1 half plus 1 is equal to 1 half times gamma of 1 half, which is equal to square root of pi over 2. So that's the value of gamma of 3 halves. And then, well, and using this recursive relation, gamma of u plus 1 is equal to u times gamma of u. And using that recursive relation repeatedly, then we can see that gamma of n plus 1 half is equal to 2n minus 1 double factorial times square root of pi over 2 to the power of 2 to the nth power for any positive integer n. So for n equals 1, 2, 3, 4, 5, and so on. Then gamma of n plus 1 half is, well, the reason why we only care about the integer value of n is because here we're just taking the sum from n equals 0 to infinity, so we only need to care about the integer values of n. We don't need to care about all real values of n. We only need to care about the integer values of n because we're taking the sum from n equals 0 to infinity. So for positive integers n, and so, well, the sum also includes n equals 0, but for now we only need to care about the positive integer values of n, so just 1, 2, 3, and so on. We will get to the 0 later. And then, so for positive integer values of n, so n equals 1, 2, 3, 4, 5, and so on, then gamma of n plus 1 half is equal to 2n minus 1 double factorial times square root of pi over 2 to the nth power. And let's simplify this a little bit more. So, well, not yet. So before we simplify the expression, so we need to find the expression for gamma of 2n plus 3 halves. And so gamma of 2n plus 3 halves is equal to gamma of 2n plus 1 half. So we will substitute n is equal to the 2n plus 1. And what we get is the gamma of 2n plus 3 halves, which is the gamma of 2n plus 1 half, is equal to, well, here when it's n plus 1 half, we get 2n minus 1 double factorial. So 2 times whatever is adding to 1 half minus 1 double factorial. So gamma of 2n plus 1 half is 2 times 2n plus 1 and then minus 1 and then double factorial. So 2 times 2n plus 1 is 4n plus 2 and then minus 1. So that's 4n plus 1 double factorial times square root of pi. And then I'm gonna zoom in on this, it's a little too small. So 4n plus 1 double factorial, that is 2 times the 2n plus 1 and then minus 1. So 4n plus 1 double factorial times square root of pi over, well, when we had n plus 1 half, we got 2 to the nth power. So here we have 2n plus 1 half, so it's divided by 2 over 2 to the power of 2n plus 1. we're just substituting n to 2n plus 1 here, and then multiplying both sides by 4n plus 2 double factorial. So I mean not both sides. So here multiplying both the numerator and the denominator by 4n plus 2 double factorial. So 4n plus 2 double factorial. Then, so what we get here is, so on the denominator, no, on the numerator, then we have 4n plus 1 double factorial times 4n plus 2 double factorial. So that is 4n plus 2 factorial. And then, well, in the denominator, we just put 4n plus 2 double factorial here for the time being, for now. So, and then this is what we get. So the gamma of 2n plus 3, 2n plus 3 halves is equal to 4n plus 2 factorial times square root of pi over 2 to the power of 2n plus 1 times 4n plus 2 double factorial. And notice that, well, maybe I should explain the multiplication of the two double factorials first. And so I'm going to use this space here. So we just did 4n plus 1 double factorial times 4n plus 2 double factorial is equal to 4n plus 2 factorial. And the reason why is, so here the 4n plus 1 double factorial is basically 4n plus 1 times 4n plus 1 and then minus 2, so that's 4n minus 1 times 4n and then minus 2, so 4n minus 3 and so on, and times 4n plus 2 double factorial. So that is 4n plus 2 times 4n, because double factorial is we multiply the numbers that are like 2 units apart from each other. So 4n plus 2 times 4n minus 2 and so on, all the way down to 1 or 2. And then if we multiply these two together, then we can see that we have 4n plus 2 times 4n plus 1 times 4n times 4n minus 1 times 4n minus 2 times 4n minus 3 and so on. So that's 4n plus 2 factorial. Alright. And then, so that's what we get after doing the 4n plus 1 double factorial times 4n plus 2 double factorial is 4n plus 2 factorial. And then this 4n plus 2 double factorial has a nice form, and that it is, and the 4n plus 2 double factorial is equal to, well, 4n plus 2 is 2 to the power of, 4n plus 2 is 2 times 2n plus 1. So 4n plus 2 double factorial is 2 to the power of 2n plus 1 times 2n plus 1 factorial. So that's why we've got 2n plus 1 factorial here, and 2 to the power of 2n plus 1 times 2 to the power of 2n plus 1 is 2 to the power of 4n plus 2 here. So finally we get, so this is the simplest form. It looks complicated, but it's the simplest form after simplifying. The most simplified form for gamma of 2n plus 3 halves. So gamma of 2n plus 3 halves is equal to 4n plus 2 factorial times square root of pi. So 4n plus 2 factorial times square root of pi times 2 to the power of, over 2 to the power of 4n plus 2 times 2n plus 1 factorial. Please bear with me, this is quite long. Usually my videos are not that long, but this one is... So, moving on to the next slide. And well, we said that that formula works for, is true for, that formula is true for n larger than or equal to 1, for n for positive integer values of n, so 1 2 3 4 5 and so on. But we also need to consider the case when n is equal to 0, and well, we just need to see that this formula which we just derived, or which we just simplified and got this formula from the last slide. And so this formula is true for positive integer values of n, and we can also see that this formula also works for n is equal to 0, because when we plug in n is equal to 0, we get, on the left hand side, we get gamma of 3 halves, which we know should be square root of pi over 2. And by that I mean square root of pi. So by that I mean square root of pi over 2, not square root of the whole thing, but just the square root of pi, and then over 2. And if we plug in the n equals 0 to the right hand side here, we get 4 times 0 plus 2 is 2, 2 factorial is 2. And then in the denominator, well, 2 to the power of 4 times 0 plus 2 is 4. And 2 times 0 plus 1 is 1. 1 factorial is 1. So it's 2 over 4, which is 1 over 2, times square root of pi. So that's correct. So this equation also works for n equals 0. And so gamma of 2n plus 3 halves is equal to 4n plus 2 factorial times square root of pi over 2 to the power of 4n plus 2 times 2n plus 1 factorial for n larger than or equal to 0. For integer values of n, of course, not all real values of n. And then the next part is the part in the, I gotta go back to the last slide. Alright, so we still have to simplify the gamma of 2n plus 3, and that is not complicated at all compared to what we just did. So well, just using the definition that gamma of n for integer values of n, then well, positive integer values of n, then gamma of n is equal to n minus 1 factorial. So gamma of 2n plus 3 is 2n plus 2 factorial. Alright, so that is, so we have simplified all of the 3 gamma terms, 3 gamma expressions. So we will substitute this, and let me go back to the last slide. Where is it? Alright, so we will substitute this expression for gamma of 3 halves, and well, back to this slide, and this expression for gamma of 2n plus 3 halves, and this expression for gamma of 2n plus 3, and substituting all those 3 expressions into the result that we got for this integral in terms of those 3 gamma expressions, then we get this integral, the integral from 0 to 1 of t to the power of 2n plus 1 half times 1 minus t to the power of 1 half dt. After putting all those 3 gamma expressions into the result that the previous result that we got for this integral, and simplifying a little bit algebraically, then we get this integral is equal to pi over 16 times 1 over 2 to the power of 4n times n plus 1 times 4n plus 2 choose 2n plus 1. And why this is the case is because, well, we got the 4n plus 2 factorial in the numerator here, and in the denominator we got 2n plus 1 factorial, and we got 2n plus 2 factorial in the denominator from the gamma of 2n plus 3 in the denominator. We get the 2n plus 2 factorial in the denominator, and well, 2n plus 2 factorial is 2n plus 2 times 2n plus 1 factorial, so we get 2n plus 1 factorial squared, in the denominator, and then in the numerator we got the 4n plus 2 factorial, and so 4n plus 2 factorial divided by 2n plus 1 factorial squared is this. 4n plus 2 choose 2n plus 1. That's the binomial, the central binomial coefficient. Well, ish. It's not really the central binomial coefficient, because the central binomial coefficient is 2n choose n, but here it's sort of something that looks similar to that, because 4n plus 2 is 2 times 2n plus 1. So here we have the 2 times 2n plus 1 choose 2n plus 1, or 4n plus 2 choose 2n plus 1. And then, well, we've got the 2 to the power 4n here, and then so 2n plus 2 factorial is 2n plus 2 times 2n plus 1 factorial, and well, we already used the 2n plus 1 factorial for this part, and well, for the 2n plus 2, that is 2 times n plus 1, so that's why we've got the n plus 1 here, and we have 2 to the power of 2 here, so that's 4, and then 4 times 2 is 8, and 8 times the gamma of 3 halves is square root of pi over 2, so 8 times 2, that's why we've got the 16 here, and then, well, we've also got the square root of pi in this expression times the square root of pi of the gamma of 3 halves, then we've got pi there in the numerator. So I'm out of breath. I'm tired. I've never made a video this long, really. I mean, maybe this is not so long, but like I have to like talk really fast to get through all these many details and equations and stuff. So yeah, I'm out of breath. Anyway, well, so the integral from 0 to 1 of t to the power of 2n plus 1 half times 1 minus t to the power of 1 half dt is equal to pi over 16 times 1 over 2 to the power of 4n times n plus 1 times 4n plus 2 choose 2n plus 1. And that is the result we get for the integral so far. Well, that is the final result we will get for this integral. And now we're going to plug this into the sum for the integral I that we're solving. Finally, we're getting close to the final answer. So, well, we will substitute this result right here into the integral I that we're solving in this video. And so we will substitute that result into this equation here, this expression here, this equation here. So I is equal to the sum from n equals 0 to infinity of -1 to the nth power times that integral, and then we're gonna substitute the result for this integral into this sum, and we get the integral I is equal to pi over 16 times the sum from n equals 0 to infinity of -1 to the power of n over 2 to the power of 4n times n plus 1 times 4n plus 2 choose 2n plus 1. So, well, let's rearrange it algebraically a little bit. And so 2 to the power of 4n is 2 to the power of 4 to the power of n, and 2 to the power of 4 is 4 to the power of 2 or 4 squared, so that's 4 to the power of, so 2 to the power of 4n is 4 to the power of 2n. And well, we want to have 4 to the power of 2n plus 1, and I'll tell you the reason why later, but we want to have 4 to the power of 2n plus 1 here, so we will take 1 4 from this, and so we only have 4 left here. So that's, so in the denominator we get 4 times 4 to the power of 2n plus 1. And then, well, -1 to the power of n is I to the power of 2n, which is I to the power of 2n plus 1 divided by I. Alright, and then still the same n plus 1, and then the same for n plus 2, choose 2n plus 1. and so this, so and then 1 over n plus 1 is the integral from 0 to 1 of x to the power of n dx. So we just put that in here, and then so we get the integral I is equal to pi over 4i of the pi over 4i times the integral from 0 to 1 of the sum from n equals 0 to infinity of I to the power of 2n plus 1 times x to the nth power over 4 to the power of 2n plus 1, choose times 4n plus 2, choose 2n plus 1 dx. And we get this simply because the 1 over n plus 1 is the integral from 0 to 1 of x to the nth power times dx. That's the basic integral. You can work that out on your own. And well, we want to have something, we want to have everything in here to the power of 2n plus 1. So x to the power of n is square root x to the power of 2n plus 1 divided by square root of x. So this is the expression that we get for the integral I. So the reason why I wanted to have the power, like everything to the power of 2n plus 1 is because, well, 2n plus 1, if you, so let s be equal to this sum that we need to solve in order to solve for the, in order to solve the integral I, we need to solve this sum first. So let s be equal to this sum. Alright, and the reason why I wanted to have all, like everything to the power of 2n plus 1 is because they will be odd terms. So when we take the sum from n equals 0, n equals 0 to infinity, then, well, 2 times 0 plus 1 is 1, 2 times 1 plus 1 is 3, 2 times 2 plus 3 is, 2 times 2 plus 1 is 5, and then 2 times 3 plus 1 is 7, and so on. So it's all odd terms. So we can break it down into the sum, or the, like the difference of alternating, of an alternating and a non-alternating series. So, well, we will go to the next slide. So for now, let s be equal to this sum. So you can see that everything here is 2n plus 1, 2n plus 1, and 4n plus 2 is 2 times 2n plus 1, and also 2n plus 1 here. So it is all odd terms. And then let's go to the next but not last slide. I'm really out of breath. This is so long. So, well, let s be equal to that sum, and then we can break it down like this. So we can break it down like this. So s is equal to, well, this. I'm not gonna spell it all out, it's so long. Maybe the best way is to just leave it like that without zooming in. So well, and you can see that the first sum here is a non-alternating series, and you can see that every 2n plus 1 is turned into n. Alright, so every 2n plus 1 is turned into n, and the first sum is non-alternating. The second sum here, the second series here is alternating because there's the negative 1 to the nth power there, so it's alternating series. And well, in the first series, everything is positive, and in the second series, well, there's the negative 1 to the nth power there, so every terms with the even indices will be positive, and the terms with the odd indices will be negative. And when we do minus like this, then, well, for the terms with even indices, positive, so here, so the even indices are going to be positive, even indices are positive, so positive minus positive cancel out. And then for the odd indices, positive minus, and then here negative 1 to the nth power, so the terms with odd indices will be negative. So positive minus the negative will be 2 times the terms with odd indices, and we divide by 2, so that we only get the terms with the odd indices. And so that is why, so that is equal to the sum that we got on the last slide, which is this, all terms with odd indices, because of the 2n plus 1. Alright, so back to the slide that we were doing. So here, so we break it down into the non-alternating series minus the alternating series divided by 2, and then at this step we can use this generating function for the central binomial coefficient, the sum from n equals 0 to infinity of 2n choose n times x to the power of n is equal to 1 over square root of 1 minus 4x. And this series can be proven using the binomial theorem or the Taylor series. And this series converges for the absolute value of x less than 1/4. Well, not exactly less than 1/4, but well, it converges for magnitude value of x less than or equal to 1/4 actually, but except for x equals 1/4. So so using this generating function of 2n choose n, then we get s is equal to 1/2 times this series. So you can see that this series is 2n choose n times, well, I times square root of x over 4, everything to the nth power. So just put them all in, and then this is what we get. And then the second series is this, which is 2n choose n times, well, negative I times square root of x over 4, everything to the nth power. So we just put that into the x here, so this is what we get. And so s is equal to, so it's just using this generating function of the central binomial coefficient 2n choose n. So s is equal to 1/2 times 1 over square root of 1 minus I times square root of x minus 1/2 times 1 over square root of 1 plus I times square root of x. So we will substitute this expression into this expression for s into this equation here to solve for I. Alright, so we'll substitute the result that we got for this series into this whole equation to solve for I. So I, then after substituting that result for the series into the equation for I, then we get I is equal to pi over 4i times integral from 0 to 1 of 1 over 2 times square root of x times 1 over square root of 1 minus I times square root of x dx minus pi over 4i times square root I'm just trying to go too fast, and I just say the wrong thing all the time. Well, minus pi over 4i times the integral from 0 to 1 of 1 over 2 times square root of x times 1 over square root of 1 plus I square root of x dx. And so that is the expression for I, so this whole thing. And then, well, these two integrals are actually easy to solve because we can just substitute square root of x into x. So it's just another way of saying substituting u is equal to square root of x without using a new variable, like using a new dummy variable for the integration. So because 1 over 2 times square root of x is exactly the derivative of square root of x, so it's easy to make that substitution. So just substitute square root of x into x, and then this is what we get. I is equal to pi over 4i times the integral from 0 to 1 of 1 over square root of 1 minus I x dx minus pi over 4i times the integral from 0 to 1 of 1 over square root of 1 plus I x dx. And well, this integral is easy to evaluate. It is simply pi over 2 times the square root of 1 minus ix, well, from 0 to 1, for x from 0 to 1, plus pi over 2 times the square root of 1 plus ix, and then x goes from 0 to 1. Plug in the values for x, and then we get this. So I is equal to pi over 2 times square root of 1 minus I plus pi over 2 times square root of 1 plus I minus pi. We're getting close. We're getting closer. Oh, this is so long. Well, so now we need to find the square roots of 1 plus I and 1 minus I. So 1 plus I is square root of 1 over square root of 2 plus I over square root of 2, which is equal to square root of 2 times e to the power of I pi over 4. Just using the Euler's formula. The Euler's formula for the, like, e to the ix is equal to cosine of x plus I sine x. And well, cosine of pi over 4 is 1 over square root of 2, and same thing for sine of pi over 4. And then 1 minus I is equal to square root of 2 times 1 over square root of 2 minus I over square root of 2, which is equal to, we're using Euler's formula, then it's equal to square root of 2 times e to the power of negative I pi over 4. And so, going to the next slide. This last slide, finally. Oh. Well, so taking the square root, then square root of 1 plus I is, well, the square root of square root of 2 is the fourth root of 2 times, well, the square root of e to the I pi over 4 is e to the I pi over 8. And then square root of 1 minus I is the fourth root of 2 times the square root of e to the power of negative I pi over 4. And so that is e to the power of negative I pi over 8. So substituting the values for square root of 1 plus I and square root of 1 minus I into, substituting those two values into this equation here for I, then we're getting close to the final answer. Oh, we get I is equal to pi times fourth root of 2 times e to the I pi over 8 plus e to the negative I pi over 8 over 2 minus pi. And this expression right here, e to the I pi over 8 plus e to the negative I pi over 8 over 2 is simply cosine of pi over 8. And then using some trigonometric identities, then we can find that cosine of pi over 8 is equal to square root of 2 plus square root of 2 and then over 2. So this is what we get for I. And then, well, just simplifying algebraically, because you can see that the fourth root of 2 is basically the square root of square root of 2. And so, and then 2 is square root of 2 times square root of, fourth root of, my brain's not really working after talking for too long and fast and getting confused. Anyway, the fourth root of 2 is square root of 2. So we will multiply, so this is the square root of 2, so we just multiply the square root of 2 into the 2 plus square root of 2 here, and we get 2 times square root of 2 plus 2. So that's 2 times 1 plus square root of 2, and then the 2 here is simply square root of 2 times square root of 2, and so in the numerator we get the square root of 2 times 1 plus square root of 2, so that's square root of 2 times square root of 1 plus square root of 2. Well, I should write it down, it's too confusing to say it. So what I mean is, so the fourth root of 2 is the square root of square root of 2. So we can multiply the square root of 2 inside the square root sign here. And what we get is the square root of 2 square root of 2 plus 2, because square root of 2 times square root of 2 is 2. And then divided by, Well, 2 in the denominator is simply square root of 2 times square root of 2. And in the numerator, the 2 square root of 2 plus 2 is, well, 2 times 1 plus square root of 2. So that's square root of 2. So that is square root of 2 times square root of 1 plus square root of 2. And then cancel out the square root of 2 from both the denominator and the numerator. So after simplifying it, this is what we get right here. So the integral I is equal to pi times square root of 1 plus square root of 2 over 2 and then minus pi. So this is our final answer. Oh my goodness. I don't even know why I did this. I guess I just wanted to do some crazy integrals once in a while. Nah, that's a lie. I did a few crazy integrals, just haven't posted them on either Instagram or YouTube yet, but will be coming soon. You'll see a few other crazy integrals pretty soon, I guess. Anyway, so this is our final answer for this integral. The integral from 0 to pi over 4 of square root of tangent of x minus tangent of x squared dx is equal to pi times the square root of 1 plus square root of 2 over 2 minus pi. Thank you for watching.